Hello everyone, my name is Niklas and my presentation today will be about locally explaining prediction behavior of neural networks on the property level, and I do this from a causal or interventional perspective. This is joint work with my supervisor Joachim Denzler from the computer vision group at the University of Jena. In this work we consider the following question: what happens if certain input properties change? How are local predictions impacted? Take for example here 3 Lime input attributions for 3 different models, 1 unbiased and 2 models with biases. Just from the attributions, it's difficult to assess which properties of the input resulted in these predictions, and global explanations on the concept level can be misleading for local predictions. Performing interventions, here for the fur color, helps us to interpret these changes or these attributions, and we formalize this using insights from the area of causality. Causality is the science for modeling and reasoning about data-generating systems, and an important tool for this purpose are structural causal models. In this work, we consider trained neural networks as a data-generating system. We describe a structural causal model for supervised learning, and we are especially interested in the predictions y hat. In particular, we are interested whether there is a connection between some properties of interest x and y hat. For more details, we refer to our paper. Existing works study this on the global level by, in principle, testing for dependence between x and y hat. This can, for example, be an explicit CI test, or it can be something like training a classifier for concepts. However, such associational explanations cannot explain what happens if we actually intervene in a property, and this holds true also for the local level. Formally, such causal queries are structured in a hierarchy of increasing power. In particular, Peirce's causal hierarchy distinguishes between associational, interventional, and counterfactual queries. In this work, we focus on the interventional level. Crucially, the causal hierarchy theorem states that in the general case, the hierarchy is strict and does not collapse. In particular, interventional queries cannot be answered from purely observational data. We need interventions. For this reason, we study local changes in the predictions y hat for changes in the property of interest x. Formally, this is expressed using the do operator. In particular, we are interested in the interventional distributions of the predictions y hat when we intervene on a property x for a specific value. However, this opens the important questions: how do we generate interventional data? How do we get input interventions? We argue that input interventions are important to enable human verifications and ensure that practitioners actually target the properties they are interested in. We identify 3 possible sources. First, acquiring new interventional data. Second, manually designing interventions. And third, generating interventional data using, for example, pre-trained generative models. In our paper, we investigate all 3 cases, but in this presentation, we will focus on the third one because it's the most broadly applicable one. To explain this in detail, we turn towards a biased toy scenario to have a running example for our explanation here. Specifically, we consider 3 models trained on 3 different datasets. We have one dataset of cats versus dogs where the fur color is not correlated with the class. We have one dataset where only dark-furred cats and light-furred dogs exist, and one dataset with the opposite bias. So models trained on the latter ones, they will show a bias where they predict based on the fur color. However, all 3 models predict very good or have a very high performance for the in-domain data. Only the biased models struggle when they have to predict on the opposite domains or on the unbiased domain. To study these models on the interventional level and figure out whether the fur color is actually a problem, we turn towards pre-trained diffusion models. We do this to edit the input image. For example, consider here the following interventional instruction: change the fur color to black for this white dog image. Using a diffusion model, we can generate outputs that align with the interventional edit instruction. In particular, in our work, we use the MGIE model, and of course, this depends on different parameters. Importantly for us is the text guidance scale, so the classifier-free guidance scale of the diffusion edit model. In particular, we want to use this to sample the intermediate states in this transition. More precisely, the diffusion model trained on magnitude of interventional data enables us sampling of the nonlinear transitions between property states. We find this important because for certain properties, the intermediate states can be the important ones. And this is also why we use the term property instead of concept. We can now take such a set of intervened images and study the local prediction behavior of our neural networks. In this case here, we show the transition for the property and how this changes the output neurons of the network. You can see that for the unbiased model, it never reaches the prediction threshold to change classes, which is the red dotted line. But for the biased models, you can see that they switch their predictions based on the fur color. We can now perform a similar analysis for other properties. Here we intervene on the background color, so we make the background darker and less illuminated. We can see little to no changes in the model outputs, indicating that the background here is not a bias, in contrast to the fur color. This observation is unsurprising, but it opens the question, how do we measure systematic change? How can we quantify the local impact of a property specifically for the predictions of a neural network? We propose to quantify the model behavior changes using the gradient with respect to the property x as a measure for change. More precisely, we use the magnitude of the gradient. Crucially, this is not an input gradient, but a gradient with respect to the property. We consider here the expectation with respect to this property. To estimate this in practice, we consider equidistant samples from the diffusion model using scales in the classifier-free guidance. This enables us to estimate this as the mean over the magnitudes for all our samples. Importantly, high values here do not necessarily mean significance. In our paper, we also propose a related shuffle significance test to confirm this. We refer to our paper for more of the theoretical details. We can now use this score to study the same behavior plots from before. On the left-hand side on the top, you can see the fur color intervention. On the left-hand side at the bottom, you can see the background intervention. On the right-hand side, you can see a table with our measured scores. We also note the significance and whether a prediction flip occurred. Overall, we find that our score correlates with prediction flips. In our paper, we also benchmark this with other local approaches and find that our score outperforms them in this aspect. Also, all models here are impacted more by the fur color than by the background. This also holds for the unbiased model, which makes sense if you consider that the object, so the dog in this case, or cat, is also in the center of the image. We also find significant changes for the background color, but the effect size here is negligible. We apply our methodology to various tasks and application domains. For example, we analyze a clip zero-shot classifier with real-world interventions that we captured, and we study a medical image classification task for skin lesions where we identify a known bias. However, for space or time constraints here, I focus on one application. We also perform a training analysis of neural networks to study how learned properties change during training. Specifically, we test or analyze various backbone architectures for a celeb A task to classify age. As a property here, we select the hair color, as hair color is a strong predictive feature for age. We find two key insights. First, pre-trained models in our analysis show higher magnitudes for the property gradients. So pre-trained models seem to learn properties more strongly during the training here. Second, again, we find that prediction flips during training are highly correlated with our measure. Our measure seems to be a good way to figure out whether our neural networks want to change predictions for a property. This indicates local impact. Additionally, we find that even pre-trained models forget learned properties again and again, also in later training stages. But more about this in our paper. With this quick overview over our results, I thank you all for your attention. I want to especially thank my colleagues. Without the support and feedback of them, this work would not have been possible. On the right-hand side, you can see the QR code to the project page, which you can scan to find links, for example, to the code and also a quick description of our work. And if you visit the WACV in person, I'm looking forward to meeting you there. Please find me at my poster to discuss interventional explanations further.